sampling, you're going to get dates all over the place. So he says there is no absolute reliable long-term radiological clock. And that is a true statement, and it is a valid statement because it has been validated. Now, constancy of decay rate is most essential to the process. Otherwise, it's worthless. Okay? So any artifacts or rocks that you date using these techniques depend upon, of course, the isotope having a decay rate that is stable over time. As I said before, we have no other way to depend upon the measurement if that's not true. Now, this all relates then, as I said a few moments ago, to the energetics of the nucleus. Okay? And that energy is a very high energy in the nucleus. It's measured in terms of millions of electron volts of energy. An electron volt is technically, you can't quite read that, but it's the kinetic energy that is required to accelerate an electron through a potential of 1 volt of electricity, right? The amount of energy required to accelerate an electron. Remember, electrons move in conductors, that's what causes electricity. The amount of energy to select that, to accelerate that through 1 volt is called an electron volt. Well, if you multiply, you know what a volt, 9 volt battery is, or 1.5 volt battery is, or 12 volt automobile battery, right? So think about that and then multiply it out 1,000,000 times. And you've got MeV, millions of electron volts, enormous energy in the nucleus. So you're going to need enormous energy to affect it, right? Isotopes of lower nuclear stability have faster decay rates. We know that for a fact. And they have much shorter half-lives. That's a testament to the fact that higher energy is right in line with what? Greater decay rate or accelerated decay rate. Second point, isotopes of higher nuclear stability have slower decay rates and, of course, longer half-lives. There's a direct correlation between the rate of decay and the amount of energy affording the stability or the instability to that particular isotopic nucleus. Now, here's an important point. Decay rates cannot be reduced. There's no way to do that. They are what they are because the energetics of the nucleus is determined by the particles in the nucleus. But they can be accelerated. So the isotopic nucleus absorbing more energy than it contains for maintaining its structural stability. That's how it's going to do it. If it absorbs more energy than what the energy that it contains to maintain its stability, then you're going to have an instability problem, right? Now, we threw this in here because it relates to the dating question. Here's some data that the people at ICR did with the RATE project when they dated the diffusion of helium out of zircons. And here is a conventional relationship here that's expanding, as you see, over a temperature range of roughly 300 to 350 degrees Celsius in a 1.5 billion year time frame. Well, the measurements they took on new sampling given to independent laboratories and then looking at those rates of decay gave a very different time frame for the same kind of data. And they gave this kind of relationship here, okay? Expands a time frame of about 6,000 years, roughly. Now, they did this based upon the diffusion rates of the helium coming out of the rocks. And the way it was treated, if you read the proceedings from the ICC with regard to the, I'll read one of the RATE project proceedings, that's the best way to get it. You'll notice that they used some diffusion equations to determine that. And there is one objection to this in some sense because those diffusion equations did not contain temperature dependence, which is a factor in exchanging the diffusion rate. However, I think by and large they're in the right time frame, even though, because this is not an enormous temperature change to enormously affect the diffusion rate. I mean, they will affect it to some degree. The thing I would be most concerned about is the instantaneous decay as that helium leaves that parent isotope is going to be an enormous amount of energy locally right there in that nucleus. So that helium is going to kick out of there at an extremely fast rate for a short period of time, of course, before it levels off. Now, if we had a way of measuring that, that would give us a much better handle, okay? So I'm not saying don't trust this. I'm saying you might be able to trust it in terms of order of magnitude. I think that's reasonable. But in terms of exactness, there would be some questions if you want to look at the technical aspects of the whole matter. Okay, another aspect of this is the sequence of events places the burden of disproof on the critics, of course, because they must explain how, if there is no truth in this model, that the data accidentally, by sheer coincidence, just happen to have fallen the right predictions of the model. That's what Russ Humphreys said. He said, we're looking at a biblical time frame within a 5,000 or 6,000 year time frame, and these data seem to be consistent with that. So he said he's presuming that it's not, that you believe, and I think you do, that they're being as honest as they can based upon the methods they use, that this was reasonably good data, and it's a reasonably good conclusion, okay? So that's what he's basing that on. Now here's another important quote by Fred Uneman. He's made this some years ago, okay?